Good evening, students. And today we will discuss about the fragmentation patterns of certain groups of organic chemistry, like alkenes, alkynes, aromatic compounds, alcohols, phenols. So we will discuss these categories today. Okay. So last class we have discussed about what are the general fragmentation patterns of alkenes. Okay. So now today alkenes. Unlike the alkenes actually gives a very nice molecular ion peak. Why? Because the double bonds can take the electronic energy. That energy can be basically delocalized. So therefore, anything that stabilizes the molecule, that will be basically corresponding molecular ion can be found in the mass spectrum. Okay, so the simple reason is that. And isomers, with the isomers, for example, alkene means we always come across the EZ configuration, right? So these type of isomers with the mass spectrometry, it is not possible. Okay, unlike other spectroscopic techniques, so this is not possible to identify the isomers using the mass spectrometry data. Okay, and the usual ions which are found in the mass spectrum are actually of the form CnH2n minus 1. Those actually came from the fragments C3H5, C4H7, C5H9, etc. And the corresponding molecular fragment masses are basically 41, 55, 69, and so on. Okay, so these are the typical, I mean, essentially you remember the 41 peak and also 55 peak correspond to 55 and there's a value 69, and these are the very common the case of alkenes. Okay, the terminal alkenes will readily undergo to the allyl carbocation, terminal alkenes. So therefore they will give a peak at m by z value 41, terminal alkenes. Okay, so that is another thing that you please remember. Why? Because they according to the stability last time as a part of quantum chemistry I had explained in terms of beta. Okay, the stability in terms of beta value we have calculated how much it is required for a carbocation, whether it is allyl carbocation or allyl radical or the anion that we have calculated, right? So it is nicely a fairly stable carbocation. Therefore, corresponding molecular ion peak can be invariably seen in the mass spectrum. Okay, and the fragmentation, the mechanism is shown here. Okay, so the terminal alkyne will readily uh, will cleave like this, and then the alkyne, the R group will leave as a radical, leaving the positively charged this type of fragment, which actually correspond to this 41. Okay, that is it. One another point. Then this is an example of cis-2-butene, cis-2-butene, and its molecular weight, as you can see here, it is at 70. You can notice the molecular ion peak, and then just adjacent to the molecular ion peak, you can find a m plus 1 peak, m plus 1 peak. Okay, and then there is some fragment, something actually fragmented from the molecular ion. Then actually you can see very intense peak, which is actually 100% at 55 number, and the 55 number actually, from 75 or 70 molecular mass, if the molecule is losing one CH3 radical which correspond to 15, then you can notice this. This is the point that we just learned. The terminal thing that will undergo this type of thing. Of course, it can also undergo like this, and corresponding peak can be observed in the same spectrum itself. Then this is another example that the 1-hexyne. This is the other example, 1-hexyl, and here you can very clearly see that the allyl carbocation formation can be observed. Okay, so 84 is the molecular mass of the 84 is the molecular mass of this particular molecule, 1-hexene, and then you can just subtract this one and then say that 69. What is the difference between the 84 and 69? It is 15. So 15 can be readily interpreted to the methyl radical. Then you can just immediately go back and then calculate what is the difference between 84 and this number. 84 and this number. This number is 50, 51, 52, 53, 54, 55, 56. At 56, we have something else. That's the something else fragment actually correspond to the cleavage of this fragment. It's already shown on the slide itself. So if it is cleaving here, that corresponds to this fragment. Okay. Similarly, the molecule can also fragment here. Okay. So there are several possibilities are there, and which fragment exactly, whether it is shown, whether it is visible in the spectrum or not, it all depends upon the fragmented ions stability in the chamber. Okay, so you can here there is a peak at 42 and there is a peak at m minus 41. Okay, 41 correspond to this allyl carbocation which we have discussed just now. What about 42? Okay, so this you can take it as an example and then work it out. Similarly, this is an example of one pentene. And the pentene molecular mass is basically 70. Then 17 actually there is a at 55 there is a peak. That's 3H3 loss of methyl radical. So this is understood. And then at 42 again there is very intense peak. And it seems to be that 42 peak is uh, the base peak, right? It seems to be it is the base peak, and just adjacent to the 42 molecular mass, then we have the at 41 there is another peak. That 41 is the line carbocation. Okay, so I'm just trying to concentrate on the more intense peaks. Okay, so in the previous two example, you try to chalk out the plan and write different ways of fragmentation patterns, and then try to see whether you can explain what fragment is exactly correspond to the 42. Okay, so you just chalk out some kind of work it out and then post your answer in the WhatsApp group. Let me see who will explain correctly both the examples. Okay, now this is an example. In fact, it is a comparative slide where the octane and one octane and then octane both molecular spectrum is shown. You can see in the octane it's an alkane. Therefore, we can always find the fragmented species which are actually of the form CnH2n plus 1. Fragments which correspond to CnH2n plus 1. In the case of alkene, CnH2n minus 1. So such type of fragments can be seen in the down spectrum. So this is one octane. The other one is the simple octane. Okay, and this is this. And loss of, in the case of alkanes, the loss of 14, which corresponds to CH2, is very common. You can see that there is a same difference between this peak. Okay, so if you try to calculate the difference between the, these lines, that means difference between these two peaks, then you can always find it is 14. The 14 corresponds to CH2. So similar type of thing we can also find here that, and we can also find that the 41 in this case it is going to be the base peak, right? And other things also there, because since it is a lengthy alkane, then you can always find different other peaks also, because that the uh, propyl radical can be, or butyl radical can be, because it's a very lengthy one, and then metal alpha rearranged product is also possible. So definitely, so different peaks can be seen in that. Then cycloalkenes. So alkenes, another category, subcategory is the cycloalkenes. And cycloalkene also shown as molecular ion peak, so without any compromise. Even if it is a cyclohexane, so we always have no problem in seeing that, because it will undergo the cleavage, so naturally it will undergo. And the retro order product is very oftenly seen, that correspond to mass number 56, is actually due to the CH2 CH. It's a kind of 1,3 butadiene, a type of 1,3 butadiene structure, right? 1,3 1 2 3 4 1 2 3 4. Okay, so 1 3 butadiene structure, and then this cycloalkene actually undergo this type of rearrangement, and then it will give this 1 3 butadiene molecular fragmented ion, plus uh, a loss of 28, which actually correspond to the CH2 CH2 ethane. Okay. And suppose on the cyclohexane, if you have, it so happen that you have some kind of R group, and these R groups actually leave as a radicals. That is something, that one principle of the fragmentation guidelines, which we have discussed, in the last class. And this is the best example of that. One methyl, one cyclohexene, one methyl, one cyclohexene, and then the molecular mass is at 96, you can see here, and then there is a peak, there is a base peak at 81, and there is another peak at this position. So what are those? There is a peak at 68 as well, and the 68 actually correspond to what? 68 actually correspond to what? This type of the retro disorder product is this one. Like in the previous case, it is simply one seen that it has undergone, right? This type of rearrangement, it is formed 1 3 butadiene. Similarly here, one methyl, since there is a methyl, that methyl will be added over there. That's all. And then one ethylene, loss of 28 peak we can see. So here there is a loss of 28 is also seen. Then next one is the alkyne. So after the discussion of alkane and alkene, then we have alkyne, where we come across the triple bonds. And in the case of alkynes also, we will see very clearly the molecular ion peaks. So there is no difference at all. And the terminal alkynes will give you M minus 1 peak, the terminal alkynes. Okay, if you have a long chain alkyne, and where if the triple bond present at one extreme and either on the left hand side or the right hand side, then it immediately lose one hydrogen, and then that will give you M minus 1 peak. Therefore, so M minus 1 peak actually one of the probability, whenever you see M minus 1 peak, then it can be alkyne. Okay, of course, it is one option, one possibility, but there are other things also there that we will discuss as we proceed. The best example is phenols. Okay, that we will come to that later after the discussion of alcohols. But please remember that M minus 1, whenever you see M minus 1 peak, that alkyne, there could be a possibility of alkyne presence, okay, or triple bond present in that molecule. And terminal alkynes form propoxyl cation. Terminal alkynes form propoxyl cation. Like the previous case alkene, the terminal alkenes actually form the allyl carbocation. Likewise, here in the case of alkynes, we say the such a carbocation as the propoxyl cation, which corresponds to M by Z 39. Okay, so this also is very common in the case of the alkynes. Okay, so this is the one example of the one pentane. As you can see, its molecular weight is 68, and then since it is a terminal, the propoxyl cation you can see at if it is cleaving here, then it will give you a peak corresponding to 39, that actually due to the propoxyl cation. And then this is a 2-pentyne. Okay, this is a 2-pentyne. It's not a terminal alkyne. It's different. Therefore, its pattern will be different. In this case, you can see the 39 peak for the propoxyl cation. Okay, so that's a point one should remember. And then the loss of methyl group, okay, methyl radical, and then corresponding peak is a very prominent one next to the one. Okay, and the other, I don't know whether you are actually noticing or not. As we have come from the alkanes, the point I mentioned with regard to the molecular ion peak was actually alkanes. Uh, Let me go back and show you that the molecular ion peak is not very prominent. Okay, molecular ion peak is here, that it's not very prominent. Okay, and when you come to the alkenes, the molecular ion peak is somewhat strong. Okay, you can see here it is strong. You can see that several examples. One hexene is the another example. One pentene is another example, and one RT is another example. And here itself you can make a comparison. The one octane and then one octane is the best example. You see the intensity. Both were recorded with uh, the same instrument, one by one after the other. One actually intensity is actually less than 10, whereas this one is about 20. So that's the difference. So this clearly shows that the the as we go from alkane to the alkenes to the alkynes, the stability of the molecular ion actually increases, and as a result, we see very intense one. And this is the best example. You can see one pentyne case, there is a clear cut 68 peak is there. This actually shows very intense one, and in fact, it is the base peak. In fact, it is the base peak. Why it is base peak? Because you can see its intensity is 100%. Any peak whose intensity is actually 100%, such a peak we say it is a base peak. Okay. A molecular ion peak can be a base peak, but molecular ion peak need not to be always a base peak. Can be, it can be. Okay. And then 2-pentyne. This is the example that we just finished the discussion. Now, the next category of the organic compounds is the aromatic hydrocarbons. And aromatic hydrocarbons we know very well, they are very stable. Therefore, invariably we see very intense molecular ion peaks when you are dealing with the aromatic compounds. Okay, so there is no doubt at all. If you if your aromatic hydrocarbon is attached with some kind of alkyl groups, it will lose hydrogen radical and it forms very stable uh, this type of fragment, C7H7 fragment, which actually the molecular weight is the fragment weight is 91. So in the case of aromatic hydrocarbons which are attached with the alkyl group, they will lose certain radicals and then they form very stable uh, carbocation that correspond to C7H7, whose fragmented molecular weight fragment weight is about 91. Okay, you can see here the ion. This ion belongs to be a tropylium ion formed from the rearrangement of the benzyl cation. Okay, formed from the rearrangement of the benzyl. The next example, with an example, it is illustrated here. It is a toluene molecule, CH3. So it will lose one radical and then it forms a CH2 cation. This cation will undergo this type of 7-membered, it will form a 7-membered ring with a 4n plus 2 6 pi electrons are there, therefore it is highly stable one to one. So this, in fact, wherever you see aromatic compound which is attached with the alkanes, okay, so it will form a tropylium cation, and in fact, it is going to be the tropylium cation is going to be the base peak. Okay? And if the chain, suppose if the alkyl chain on the aromatic ring is fairly lengthy, then it will undergo McLafferty rearrangement. Okay, that is another point one should remember. Then there is an example of aromatic hydrocarbons, xylenes. Okay, xylene, paraxylene. Paraxylene has a 2-methyl group and at the para positions are 1,4 positions. Okay, its molecular weight is 106, and as you can notice here that loss of the 15, it is 15, right? 15 is the difference between this base peak and the molecular ion peak. Okay, so one methyl radical, if the paraxylene is losing, that we will get a very stable tropylium carbocation. Okay, this is the mechanism for that. And N-butyl benzene. N-butyl benzene is one example where it has a very lengthy alkane on the aromatic ring. Okay, so therefore, as per the point which I have discussed, it will undergo the McLafferty rearrangement. It will undergo McLafferty rearrangement. Okay, so we can write down the mechanism for that. You can see here. Just write. Okay, you just extrapolate. So what is the McLafferty rearrangement? So alpha, beta, this is gamma. So gamma positions, if you have a proton, and this type of one, it will undergo this type of rearrangement, then corresponding fragment, whatever it is formed, this we say McLafferty fragment. This fragment, in fact, it is going to be, most of the cases, it is going to be the base peak. Okay, it is going to be the base peak. So it will lose after the rearrangement, McLafferty rearrangement, it will lose one neutral species, and then it will form a odd electron species. And that odd electron species, what we call it as a McLafferty rearrangement product or fragment. That fragment, most likely, in most of the cases, it is going to be the base peak. Okay, and on the other hand, it can also undergo this type of fragmentations, like in the case of aromatic compound, which are having some type of alkane substitutions, then it can also cleave here, and then it can form, and this it will go as a radical, and then leaving this as a carbocation, right? The CH2 plus, and this is nothing but the benzyl carbocation. This benzyl carbocation actually will undergo rearrangement, and it forms the tropylium carbocation, which is very stable, that you can see in the mass spectrum. The next category of the molecules is alcohols. Alcohols, there are a couple of points one should very thoroughly understood and remember also. Okay, so the additional mode of fragmentation will cause lower molecular ion than for the corresponding alkanes. Okay, uh, along with the, you can just compare alkane and then it's a homologous alcohol. Okay, and then we always see the additional fragments. Okay, so always we will see additional fragmentation, but in the case of alkanes we see more the additional fragmentation, but as compared to the alkanes, corresponding alcohol will not be having so much of fragmentation. Okay, that is one point. And then the largest alkyl group will be as a radical. That is the one interesting point and very important point one should remember. The largest group, the longest group, or the largest group will usually leave as a radical, leaving the other one as a carbocation. So the best example, this is very unique signature of a alcohol, that CH2OH plus, that correspond to 31. This 31 is very common in the primary alcohols. When it comes to the secondary alcohols, Okay, it will form this type of peak, right? CH3, CH2, OH plus. So that is 45. So the 45 peak is very common. Similarly, in the case of H3 alcohols, the 59 peak is also very much common. Okay, so 31, 45, 59 are the usually peaks that we observe in the case of alcohols. So primary alcohols, if you are dealing with the primary alcohol, 31 is the very symbolic peak. Okay, you can just uh, immediately jump to a conclusion. Then since it is alcohol, we have the OH, and then OH can actually leave as a neutral species, taking a hydrogen from the elsewhere, right? That's also possible, especially if you have a proton at the fourth positions, and it's really possible. So 1,2 elimination occurs from hot surface ionization ceremony, and 1,4 elimination occurs from the ionization. So both 1,2 and 1,4 eliminations are very common in the case of alcohols. As a result, it actually it will lose, it will give a peak at m minus 18. M minus 18. If it is a 100 molecular weight and then 18 minus, that means at 82. At 82, you will see very like a molecular one peak, one fragmented peak. Okay, and then long chain alcohols again. This again will undergo this type of McLafferty type of rearrangement, and then that product is going to be the somewhat very stable one. Okay, very stable one, and it will found with a good descent intensity in the mass spectrum. Okay, so this is an example of that. Okay, this is another example of that. Okay. So McLafferty rearrangement. So whenever you see, this is very common and very easy also. You should practice that, how to do it. Alcohols we are discussing. Alkenes we discussed already. Alkenes, aromatic hydrocarbons we discussed, McLafferty. And it will come out. If you have a amide, if you have a all the carboxylic acids, whatnot. So whenever you see a proton at the gamma position to a heteroatom, right, or a ring, okay. So those molecules will undergo the McLafferty rearrangement, and corresponding peaks can be observed in the molecular spectrum. Alcohols. Another thing is that alcohol, in the case of alcohols, we just assume since there is a OH, we thought like hydrogen radical is fairly easy to eliminate or cleave from the molecule, and it will give M minus 1 thing. No, that is not favored actually. That is a very crucial point. Okay, so sometimes we confuse ourselves. Somewhere used to ask the question that which are the ones that doesn't give the M minus 1 peak. Always people will think that the alcohol OH is there, so hydrogen radical it will leave, therefore it will be, so that can be our choice. No, that is not the case. So alcohols actually do not give M minus 1 peak, whether it is a primary, secondary, or tertiary. Please remember that. And cycling of alcohols fragment by similar pathways, like alpha cleavage is possible. This is one of the points that I already mentioned in the previous class. Alpha cleavage next to the heteroatom is very, very common thing in the mass spectrometry. Okay, alpha cleavage next to the heteroatom. Okay, so this is one way of cleavage. Let me, so this is one way of cleavage, another way of cleavage. So there are both ways this ring can actually break and then give corresponding fragments and corresponding peaks in the spectrum. Okay, and of course the cyclic alcohols, they also undergo like the acyclic alcohols, they also undergo the dehydration. Therefore, corresponding M minus 18 peak is very common. This is an example of N-pentanol. So it is a acyclic alcohol. You can see that Unlike the other cases, the molecular ion peak, you can't see that. This is the first point I mentioned. Unlike the previous case, we can't find the molecular ion peak in the case of uh, alcohols. Okay, there should be a peak at 88, but there is no peak at all. Then what else? We have a peak at 42, and we have a peak at 55. We have a peak at 70. So these are the different peaks. Yeah, we have these are the different peaks of n-pentanol, and you can always write down. You can see that this 42 most likely it is going to be a McLaughlin rearranged product. Okay, and then this 55 is the radical cleavage, right? The pentanol is there, the alkyl chain can cleave. Okay, so this 18 is another symbolic thing I forgot to mention. So the M minus molecular ion peak is at 88, but 70. So the difference is actually 18. That 18 corresponds to the water. Then the 42 peak actually, as I told you, that this actually corresponds to this type of allyl carbon cation, that is 42, right? And then the water molecule is 18 and this is 28. So M minus 18 and M minus 28. So these are some of the peaks that we can always find with regard to the alcohols. And please remember that since it is a primary alcohol, there is a loss of the CH2 OH. CH2 OH. OH is 17, CH2 is 14. That corresponds to 31. CH2 OH carbocation. That is very much visible here. That clearly indicates that the alcohol is the primary alcohol. Suppose if it is a secondary alcohol, we will see a peak at 45, right? So please remember those numbers. And this is the 2-pentanol. 2-pentanol is it a primary or secondary? Of course, it's a secondary. And then you can see the peak, corresponding peaks. Okay, so again, you can find there is a peak at what is that? 45. There is a peak at 45. What is that 45? That 45 actually is because of the alpha cleavage to this. Okay, alpha cleavage to this. And then there's 2-methyl 2-pentanol. This is an example of that. And the corresponding peaks are already shown in this. Then cyclopentanol. Cyclopentanol. So this is another example. So in the case of cyclic uh, alcohols only, so we may get some kind of stability and therefore corresponding molecular ion can be observed. Okay, acyclic alcohols did not give molecular ion. Please remember that previous two cases. But the cyclopentanol is a cyclic one, then where it gives the molecular ion peak. Okay, what about the difference between this and that? 57 minus 86. What is the difference? The 3 plus 16, so 19. 19 refers to what? What is this peak actually? What is this peak? Can anybody say? The peak is because of that. The peak is because of that. Cyclopentanol, the one radical, ethyl radical will leave, leaving the other one with a 57 number. So please remember that. And phenols have uh, cyclic compounds, and this is a very drastic difference between the phenols and alcohols. Alcohol do not give you M minus 1 peak, but the phenols give M minus 1 peak. Okay, M minus 1 loss is can be a phenol also. Previously, I mentioned that the alkynes, terminal alkynes especially, they can easily, readily undergo the hydrogen radical elimination, and then corresponding M minus 1 peak can be observed. But in the case of phenols, the same thing happens, but not with the alcohols. Okay, please note down that. Why? Because in the case of phenols, that if it loses a hydrogen radical, then it stabilizes more, right? The phenoxide is a highly stable one. Therefore, we get very then we get the corresponding peaks in the spectrum. Okay, and the mechanism is shown here. And then similarly, in the case of aromatic, the alcohol, that is phenols, the loss of CO corresponding to 28 again. CO correspond to 28. Carbon is 14, 14 plus 16, it is 28. So, sorry. Yeah, so loss of 28 can also be due to the carbonyl functional group. Similarly, loss of formyl radical, that is basically HCO, is also observed in the case of phenols. Okay, so phenols can give, what are the peaks? Phenols can give the first peak -1 because of the loss of hydrogen radical, and then it can leave, it can eliminate a CO, okay, that is 28, and it can eliminate 29 carbonyl. So these are the common things that one should remember. And unlike the other alcohols, they give nice intense molecular entropy. That is the fourth point one should remember. Unlike the previous cases, alcohols are not very uh, good. Alcohols doesn't give very prominent molecular entropy except the cyclic pentanone case. Okay, the acyclic one doesn't give at all. But you can see here that the phenols will give very intense, and in fact is the base peak for the molecular ion itself is the base peak. Okay, and then you can see always the loss of CO, loss of HCO. You can see 66 and 65. You can find the peaks. I think there is one more thing there. Benzyl alcohols is the another example. Benzyl alcohols is the another example. So ring expansion to tryptophan is very common. Okay, ring expansion and then becoming the phenols. Tryptophanol, tryptophanol is the very common thing in the case of benzyl alcohols. This is the benzyl alcohol. Okay, so this will undergo some type of rearrangement, and then ring expansion takes place. But also the benzyl propyl the carbocation. Okay, and the other peaks, as usual, you can see CO, loss of CO, 28, and loss of water, loss of hydroxyl radical. So those peaks also you can find here. Okay, right. I think with this I stop here. Ethers onwards, so we will discuss in the next class. That is on day after tomorrow morning, and most likely I will be finishing the discussion on there itself. Okay, so if you have any doubts, you can unmute and then ask. Otherwise, we will conclude today's class.